In the previous video, we examined what generative AI is, how it works, what it can produce, and why its outputs behave as they do. We looked at the relationship between foundation models, generative capabilities, and the applications through which those capabilities are made useful. We also examined tokens, context windows, model settings, multimodality, professional applications, limitations, and the emerging distinction between systems that generate information and AI agents that can increasingly use tools and take actions. That gave us an understanding of the technology. But understanding what generative AI can do is only the first step. The next question is how those capabilities should actually be used in professional and organizational settings, and how a generative AI system can move from an impressive demonstration to something that performs useful work reliably. This brings us to the subject of this second video, using and deploying generative AI. At its simplest, using generative AI can appear remarkably straightforward. A person opens an existing application, provides a prompt or some information, receives an output, reviews the result, and perhaps modifies the instruction until the output better meets the objective. This approach is already being used for activities such as drafting, summarization, research support, software coding, image creation, translation, analysis, and many other forms of knowledge work. For many individual tasks, this relatively simple interaction may be sufficient. A professional who wants help preparing a first draft, summarizing a document, generating alternative ideas, or reorganizing information may not need to build any additional technology. The generative AI application already provides the interface, model access, and many of the supporting capabilities required to perform the task. Organizational deployment, however, can become considerably more complex. A company may want a generative AI system to work with proprietary documents, customer information, databases, enterprise applications, internal policies, or operational workflows. The system may also need to satisfy requirements relating to accuracy, privacy, security, response time, cost, regulatory compliance, reliability, and scale. At that point, the problem is no longer simply whether a model can generate an acceptable answer. The organization must consider the entire system within which the model operates. It must decide what information the model can access, where that information comes from, how the application will interact with existing software and workflows, how performance will be measured, what controls will apply, and where human review or approval will remain necessary. This distinction is important because access to a powerful model does not automatically create an effective generative AI solution. Different tasks require different levels of capability, context, speed, specialization, security, and control. A model that performs extremely well for one workload may be unnecessarily expensive or poorly suited to another. A large general-purpose model, for example, may be appropriate when the task involves complex reasoning across many different subjects. A smaller or more specialized model may be sufficient for a narrow, repetitive activity that must be performed quickly and economically at very high volume. An application working with public information may have different infrastructure requirements from one handling confidential organizational records. The same principle applies to deployment. Some organizations may obtain everything they need from an existing generative AI application or a managed model service. Others may need to connect the model with organizational information through retrieval-augmented generation, integrate it with enterprise applications, customize it for a particular task, or operate parts of the system within a more controlled environment. The appropriate solution, therefore, depends on the work that needs to be done. This leads to one of the most important principles we will use throughout this video. Start with the use case, not the technology. Instead of beginning by asking which model is the most powerful, the more useful question is what problem, task, or process we are trying to improve. Once that objective is clear, we can determine what generative AI capability is required, what information the system must use, what quality of output is acceptable, and what level of speed, cost, security, and reliability the application must achieve. We can then ask more specific questions. Does the task require a general-purpose model or a specialized one? How much information must the model process at one time? Does the application need to work with text alone, or must it also interpret images, audio, video, or other forms of information? Does it need access to current or proprietary organizational knowledge? The deployment environment must also be considered. The model might be accessed through a managed cloud service, operated on infrastructure controlled by the organization, distributed between cloud and local systems, or deployed on a device where low latency or privacy is particularly important. These choices affect cost, performance, security, scalability, and the amount of technical responsibility that the organization must assume. Data is another part of the deployment problem. A generative AI system cannot provide reliable organizational knowledge merely because the underlying model is powerful. If the application depends on enterprise information, that information must be accessible, relevant, sufficiently current, properly governed, and supplied to the system in a form that can be used effectively. Evaluation then becomes essential. A model may perform strongly on a public benchmark and still fail to meet the requirements of a particular organization or professional task. What matters in practice is whether the complete application performs the intended work with sufficient quality, accuracy, relevance, safety, speed, and consistency for the environment in which it will operate. This means that using and deploying generative AI involves a sequence of connected decisions. The business problem helps define the workload. The workload influences the choice of model. The model and workload influence the deployment environment and infrastructure. Data, security, cost, and organizational requirements shape those choices further, while evaluation determines whether the resulting system is actually fit for purpose. In this video, we will follow that progression. We will begin by examining the principal ways in which generative AI is being used across professional and organizational work. From content creation and automation to software development, information analysis, decision support, engagement, and personalization. We will then examine the two broad routes through which generative AI can be adopted. One route uses existing applications and adapts them to particular tasks through prompts, information, and human review. The other goes further by integrating or customizing generative AI around organizational data, software, workflows, and business processes. From there, we will turn to the selection of models and infrastructure. We will examine why there is no single best model for every task, why model choice and infrastructure choice are related but different decisions, and why organizations must balance capability, context, latency, control, security, adaptability, and cost. Finally, we will examine how generative AI systems should be evaluated. We will see why evaluation must reflect the actual use case, why different systems require different forms of testing, and why evaluation should continue as prompts, models, data, applications, and workflows change. The central idea throughout this video is therefore straightforward. Successful generative AI deployment does not begin with the model and then search for somewhere to use it. It begins with the work that needs to be improved, and then builds the appropriate combination of capability, model, data, infrastructure, evaluation, and human involvement around that objective. With that foundation established, we can begin with the most practical question of all: how is generative AI actually being used? In the previous section, we saw that successful deployment begins with the work that needs to be improved rather than with the technology itself. Once the problem or objective is clear, the next question is what role generative AI can actually play within that work. Generative AI can be used at several levels. At the simplest level, an individual may ask an AI system to draft a document, summarize information, create an image, explain software code, or prepare an initial analysis. At a more advanced level, an organization may integrate generative AI with its own data, software, workflows, and business processes so that the technology becomes part of a larger operating system. Although the applications are extremely diverse, they can be understood through 5 broad forms of use: creating new content, assisting and automating work, building software and digital products, analyzing information and supporting decisions, and engaging or personalizing communication. These categories often overlap, but they provide a useful way of understanding where generative AI creates practical value. The first and most visible use is the creation of new content. A user provides instructions describing the desired result, and the system generates an initial output. Depending on the model and application, that output may be text, images, software code, audio, speech, music, video, designs, or other forms of generated information. A marketing professional, for example, may provide information about a product, the intended audience, the desired tone, and the communication objective. Generative AI can then produce advertising copy, social media material, product descriptions, campaign concepts, or alternative versions adapted for different audiences. A designer may provide a written description, visual style, dimensions, and design constraints, and receive illustrations, concept designs, or visual alternatives. The same pattern increasingly appears in video production. A creator may use generative AI to help prepare a script, generate images, produce a voiceover, create video elements, assist editing, and localize the finished material for different languages or audiences. The value in each case lies partly in accelerating the movement from an idea to a first usable version, after which a person can evaluate, refine, and approve the result. The second broad use is to assist and automate parts of existing work. Here, the objective is not necessarily to automate an entire job. Instead, generative AI performs specific activities that consume time and can be accelerated without transferring complete responsibility for the work to the machine. This may include drafting, summarizing, translating, extracting information, preparing reports, creating documentation, producing meeting summaries, generating routine communications, preparing first drafts, restructuring information, or converting material from one format into another. A common workflow therefore begins with a person defining the objective. The AI performs an initial production or knowledge processing task. The person evaluates the result, the AI revises or expands it where necessary, and the person approves the final output. The productivity gain comes from reducing the amount of routine intellectual production required from the human while retaining human judgment for the parts of the work that depend on context, expertise, and accountability. The third broad use is building software and digital products. Generative AI is increasingly becoming part of the software development process. Developers can use it to generate code, autocomplete code, explain existing programs, identify possible defects, produce test cases, prepare technical documentation, translate between programming languages, and assist with the modernization of older applications. The workflow again illustrates the collaborative nature of the technology. A developer describes a requirement, the AI proposes code or a technical approach, the developer reviews and tests the output, the AI may help identify or correct problems, and the developer validates and deploys the final solution. Generative AI can therefore accelerate software development, but software quality, security, testing, architecture, and deployment decisions remain professional responsibilities. The fourth use is analyzing information and supporting decisions. The word generative can create the impression that the technology is concerned mainly with producing new content. But generative AI can also help people work with very large amounts of existing information. A system can summarize documents, compare information from several sources, extract important facts, identify themes, explain complex material, synthesize findings, organize alternatives, and generate reports that make information easier for people to interpret. In this role, generative AI acts as a bridge between information abundance and usable knowledge. Consider a product manager who has received hundreds or thousands of customer comments. Reading every comment manually may be possible, but it can be slow and difficult to do consistently. Generative AI can help organize the feedback, identify recurring issues, categorize themes, summarize customer concerns, and suggest areas that may require further investigation. The product manager can then examine the evidence, evaluate the recommendations, and decide what action is appropriate. The same principle applies to research and professional knowledge work. A research question may lead to the collection of a large number of documents. Generative AI can assist with extracting information, summarizing individual sources, comparing findings, identifying patterns, and preparing an initial synthesis. The expert then verifies the evidence, interprets its significance, challenges weak conclusions, and decides what should be incorporated into the final analysis. This distinction is important. Generative AI can support decision-making by organizing and presenting information, but generating an analysis is not the same as making the decision. Where consequences are significant, the professional remains responsible for evaluating the evidence and exercising judgment. The fifth broad use is engagement, communication, and personalization. Generative AI can generate different responses for different individuals, making it possible to adapt communication at a scale that would previously have required much more human effort. Customer service provides a clear example. A generative AI system may interpret a customer's natural language question, consult available information, generate a relevant response, summarize previous interactions, prepare follow-up correspondence, and adapt its communication to the particular situation. The result is no longer simply a text generation tool. It becomes an interactive service that combines language generation with retrieval, customer context, organizational knowledge, and workflow rules. Personalization can also be used in marketing, education, employee training, and other forms of communication. The same body of training material, for example, can be explained differently to a beginner, an experienced professional, a manager, or a technical specialist. A marketing message can be adapted according to language, audience, location, customer needs, or communication channel while preserving the same underlying objective. These 5 forms of use appear in different combinations across professions and industries. Marketing and communications rely heavily on creation, adaptation, and personalization. Customer service combines generation, retrieval, and interaction. Education combines content creation, tutoring, explanation, and personalized learning. Healthcare and life sciences use generative AI for documentation, information synthesis, communication, scientific research, and the generation of candidate molecular structures that require further investigation. Financial services can use the technology to summarize information, prepare documentation, generate reports, assist customer communication, and support analysis. Manufacturing and product development can use it to generate and compare design alternatives, consolidate customer feedback, assist supply chain information access, and support movement from requirements through design, evaluation, and refinement. Legal, compliance, and administrative work provides another useful example of the boundary between assistance and decision-making. Generative AI may retrieve, organize, summarize, compare, or draft information from contracts, regulations, policies, and other documents. But the appropriate operating model is not for the AI system to make the legal or compliance decision. The professional examines the evidence, interprets the relevant requirements, and remains responsible for the judgment. The same principle applies in human resources. Generative AI may help summarize resumes, prepare recruitment materials, create onboarding content, personalize training, or produce templates for performance reviews. But employment decisions have consequences for individuals and organizations and therefore require appropriate human oversight and organizational controls. Across all these examples, a common pattern begins to emerge. Generative AI can create new material, accelerate routine work, help build software, organize information, and personalize interaction. But the most useful deployment model is rarely simply to hand an entire professional activity to the AI system. Instead, the technology is usually inserted into a workflow. Some steps are performed by the AI because machines can generate, summarize, retrieve, transform, or process information quickly and at scale. Other steps remain with people because they require context, expertise, interpretation, accountability, relationships, or judgment. This is why the same generative AI capability can support very different applications. Text generation might be used to prepare a marketing message, explain a technical concept to a student, draft a customer service response, summarize a legal document, or produce an initial research report. The underlying capability may be similar, but the surrounding information, workflow, controls, and human responsibilities are different. Understanding how generative AI is used therefore leads naturally to the next deployment question. Once an individual or organization has identified a useful application, how should that capability actually be adopted? There are two broad routes. One is to use an existing generative AI more deeply around organizational data, software, workflows, and business processes. In the next section, we will examine these two routes and see why the choice between them should again begin with the use case rather than with the technology. In the previous section, we examined 5 broad ways in which generative AI is being used: creating new content, assisting and automating work, building software and digital products, analyzing information and supporting decisions, and engaging or personalizing communication. We also saw that these uses appear in different combinations across professions and industries, and that the technology usually becomes most useful when it is inserted into a workflow rather than treated as a replacement for the entire activity. Once a useful application has been identified, the next question is how generative AI should actually be adopted. For an individual or an organization, there are 2 broad routes. The first is to use an existing generative AI application. The second is to integrate or customize generative AI more deeply for a particular workflow, organizational process, or business application. The first route is the simpler and more accessible one. A person selects an existing application, provides instructions and relevant context, reviews the generated output, refines the prompt where necessary, revises the result, and then decides how it should be used. This is the pattern already familiar to millions of people using generative AI for writing, research, coding, design, analysis, summarization, and many other tasks. The main advantage of this approach is speed. The user does not need to build an AI system or develop the underlying model. The application already provides access to generative AI capabilities through an interface, and the user adapts those capabilities to a particular task through prompts, information, iteration, and human review. Consider a consultant preparing an initial analysis. The consultant may provide a question, some background information, perhaps a document or data set, and instructions describing the desired output. The generative AI system produces a first response. The consultant examines the result, identifies gaps or weaknesses, provides further instructions, and continues the interaction until the material becomes useful. The same pattern can be applied to many professional tasks. A marketer can generate alternative campaign messages. A teacher can prepare explanatory material at different levels of difficulty. A software developer can request code suggestions or debugging assistance. A researcher can use the system to help summarize and compare documents. In each case, the existing application provides the capability, while the user supplies the objective, context, judgment, and final decision about how the output should be used. This route can therefore produce substantial value without requiring an organization to create a customized AI architecture. It is particularly attractive when the task is relatively self-contained, when the information required can be supplied directly to the application, and when the user can review the output before acting on it. The second route goes further. Instead of using generative AI primarily as a standalone application, an organization can integrate or customize it around its own information, software, workflows, interfaces, security systems, and organizational rules. This changes the role of the technology. Generative AI begins to move from being an external productivity tool toward becoming part of the organization's operating environment. Imagine, for example, a customer service application. A general-purpose generative AI system may already be capable of understanding questions and generating answers, but an enterprise customer service system may need access to product information, account records, service policies, previous customer interactions, and internal procedures. It may also need rules governing what information may be disclosed, when a request should be escalated, and when a human employee must take over. The underlying generative capability remains important, but the surrounding system becomes equally important. The application must connect the model with the information and controls required for the business process. The same principle applies to an internal knowledge assistant. A general-purpose model may possess broad knowledge, but an employee asking about an organization's current policies, technical procedures, project information, or internal documentation needs answers grounded in information that may never have been part of the model's original training data. The organization may therefore connect the model with approved internal sources so that relevant information can be retrieved when a question is asked. This is one of the reasons retrieval-augmented generation can become important in enterprise deployment. Instead of expecting the model to contain every piece of current or proprietary information within its trained parameters, the application retrieves relevant information from an external knowledge source and provides that information to the model as part of the context used to generate the answer. Integration can go further still. Generative AI may be connected with databases, business applications, workflow systems, or specialized interfaces. At that point, the system is no longer simply responding to an isolated prompt. It becomes one component within a larger process. The progression can therefore be understood as a continuum. An organization may begin with a general-purpose generative AI tool, use prompts to adapt it to a particular task, customize it with organizational information, integrate it into a workflow, and eventually embed it within a business application. As the level of integration increases, the potential value can increase, but so does the complexity. More integration means more decisions about data access, security, application design, infrastructure, monitoring, evaluation, and responsibility. The organization must decide not only what the model can do, but also what information it is permitted to use, which systems it can interact with, what outputs are acceptable, and where human oversight is required. This brings us back to a principle introduced in the previous section. The correct starting point is not the technology, it is the use case. Organizations can easily fall into the trap of beginning with the question, where can we use generative AI? That question encourages people to search for problems that can be attached to a technology they already want to deploy. A more useful question is, what problem, task, or process are we trying to improve, and which generative capability can help? The difference may appear subtle, but it changes the entire deployment process. The first question begins with the technology and searches for an application. The second begins with an objective and then asks whether generative AI is an appropriate way to achieve it. A practical sequence therefore begins with the problem or objective. The organization identifies the task that needs to be improved and determines what generative capability may be useful. It then considers the appropriate model or application, the data and context that must be supplied, the output that will be generated, how that output will be evaluated by people, and how the capability will eventually fit into the wider workflow. Consider a company that wants to reduce the time employees spend searching through internal policy documents. Beginning with the technology might lead to a general objective such as building an AI assistant. Beginning with the use case produces a much more precise problem. Employees need to locate accurate answers from approved internal policies quickly and consistently. That formulation immediately raises more useful design questions. Which documents are authoritative? How frequently do they change? Who is permitted to access them? Should the system provide the source supporting each answer? What happens when the relevant information cannot be found? Which questions require referral to a specialist rather than an automated response? Once these requirements are understood, the organization can decide whether an existing generative AI application is sufficient or whether a more integrated solution is required. It can also begin to determine what model capabilities, retrieval technology, data architecture, security controls, evaluation methods, and human responsibilities will be needed. The same reasoning applies to a creative task, a software development process, a customer service operation, a research workflow, or an internal administrative function. The appropriate technology follows from the requirements of the work. This use case first approach also helps prevent unnecessary complexity. Not every application requires a customized model, proprietary infrastructure, or deep enterprise integration. If an existing application can perform the task safely, economically, and effectively with appropriate human review, building a more elaborate system may add cost without adding equivalent value. Conversely, some tasks cannot be performed adequately through a standalone application. If the system must use proprietary data, operate at high volume, meet strict privacy or latency requirements, interact with enterprise software, or produce outputs that must satisfy specific organizational standards, deeper integration may be justified. The two adoption routes should therefore not be viewed as competing alternatives where one is inherently more advanced or desirable. They represent different levels of integration suited to different kinds of work. A single organization may use both at the same time, allowing employees to use general-purpose generative AI applications for some activities while developing integrated systems for selected high-value or repeatable workflows. The central question is always the same. What combination of capability, information, integration, control, and human involvement is appropriate for the task? Once that question has been answered, the next deployment challenge becomes clearer. Whether an organization uses an existing application or builds a more integrated system, it still has to decide which generative AI model is best suited to the workload. There is no single model that is best for every purpose. Different models vary in capability, size, specialization, context length, modality, speed, cost, and the level of control they provide. Selecting the most powerful model available may therefore be neither necessary nor economical. In the next section, we will examine how generative AI models should be selected, why task fit matters more than popularity, and how organizations can choose between large and small models, general purpose and specialized models, and open and proprietary approaches according to the requirements of the work. In the previous section, we examined the two broad routes through which generative AI can be adopted. An individual or organization can use an existing generative AI application and adapt it through prompts, context, iteration, and human review. Or it can integrate generative AI more deeply with organizational data, software, workflows, and business processes. We also saw that the correct starting point in either case is the use case rather than the technology. Once the problem and the intended use are clear, the next question is, which model is best suited to the workload? This is where organizations can easily make another mistake by assuming that the largest, newest, or most widely discussed model must automatically be the best choice. There is no single generative AI model that is best for every task. Different models are designed with different capabilities, strengths, limitations, context lengths, modalities, deployment options, and cost structures. The relevant question is therefore not which is the most powerful model. It is which model can perform this particular workload with the required quality, speed, cost, security, and reliability. Model selection begins with the task itself. The organization first needs to define what the system will actually be expected to do. The task may involve conversation, summarization, code generation, document analysis, reasoning, retrieval augmented generation, multimodal processing, or more complex agentic work. Each of these places different demands on the model. The complexity and consequence of the task also matter. Generating several alternative marketing headlines is very different from analyzing a large collection of technical documents or supporting a professional decision. A task requiring nuanced reasoning, long-form synthesis, or interpretation across several sources may require capabilities that are unnecessary for a narrow and repetitive workflow. The required output must also be considered. Does the application need a short factual answer, a detailed report, software code, structured data, an image, or a combination of several forms of information? Does it need to follow a precise format or professional style? Does it need specialized terminology or knowledge from a particular domain? These requirements help determine the class of model that should be considered. Response time is another factor. Some applications can tolerate several seconds or more while a complex response is generated. Others may need to respond almost immediately because they are embedded in a customer interaction, operational process, or real-time application. A model that provides exceptional capability but responds too slowly may still be unsuitable for the intended workload. The amount of information that must be processed at one time is also important. As we saw in the first video, models have context windows that limit the amount of information available within a particular interaction. An application that works with long documents, extended conversations, large code repositories, or several sources at once may therefore need a model with a larger context capacity. But a larger context window should not automatically be treated as better. Processing more information requires more computation and can increase cost and response time. The model should therefore have enough context for the task without introducing unnecessary overhead. Modality creates another important selection question. Some workloads involve text alone. Others may require the model to interpret images, diagrams, charts, audio, video, or combinations of these formats. A model selected for a document analysis application may therefore need different capabilities from one used for image generation, software development, or multimodal technical support. Once the workload has been defined, organizations can begin comparing different classes of models. One important distinction is between large general-purpose models and smaller or more specialized models. Large foundation models generally provide broad versatility. They can perform many different kinds of tasks and are often better suited to complex, nuanced, or multi-step work. Their broad training can make them useful where the range of user requests is difficult to predict or where the application must work across many domains. That versatility, however, comes with costs. Larger models generally require more computing resources, more memory, and more inference capacity. They may take longer to respond and may cost more to operate, particularly when the system must serve large numbers of requests. Smaller or specialized models offer a different trade-off. They may have a narrower range of capability, but they can perform well on defined tasks or domains, particularly when they have been adapted or tuned for the required work. Because they require fewer computing resources, they can also be faster and less expensive to operate. Consider a high-volume enterprise application that performs the same narrow task millions of times. Using a very large general-purpose model for every request may provide capabilities that the application never needs. A smaller model that reliably performs the required tasks could provide a better balance between quality, speed, and cost. The opposite may be true for complex professional work. If the system must analyze several documents, understand ambiguous instructions, reason across different subjects, and produce a nuanced synthesis, the broader capabilities of a larger model may justify the additional cost. Model size should therefore follow task complexity rather than prestige. The objective is not to maximize model capability regardless of need. It is to use sufficient capability to meet the required performance threshold. Another distinction is between general-purpose, domain-specific, and task-specific models. A general-purpose model is designed to handle many different types of work. A domain-specific model is adapted to a particular field or body of terminology, while a task-specific model focuses more narrowly on a defined function such as translation, code completion, classification, or image generation. A specialized model may be attractive where the workload is stable and repeated. A general-purpose model may be more appropriate where flexibility is important or where users are likely to ask a wide range of questions. Once again, the decision depends on the characteristics of the use case. Organizations must also decide between open and proprietary models. Open models can provide greater control over customization and deployment. They may allow an organization to tune the model more extensively, operate it within its own environment, and exercise greater control over how the system is configured. That flexibility also transfers more responsibility to the organization. The organization may need greater technical expertise and may have to take more direct responsibility for licensing, deployment, privacy, security, guardrails, monitoring, and compliance. Proprietary models can reduce some of this management burden. They are often offered through managed platforms or application programming interfaces and may include enterprise support, security features, safety systems, documentation, and commercial arrangements that simplify adoption. The trade-off is reduced control over some aspects of the model and greater dependence on the provider's platform, pricing, availability, and product roadmap. For this reason, Organizations do not necessarily have to make a permanent choice between open and proprietary models. Different models can be used for different workloads, and some enterprises may operate a mixture of both. Selecting a model therefore involves balancing several dimensions at the same time. Task fit, reasoning complexity, context length, modality, specialization, speed, cost, control, security, and deployment flexibility can all influence the decision. This is why model selection should not be based on reputation alone. A model may perform exceptionally well on public benchmarks and still fail to meet the needs of a particular application. The only reliable way to determine suitability is to test candidate models on the actual kinds of work they will be expected to perform. A practical evaluation begins by defining the requirements and acceptance criteria for the workload. Candidate models can then be given the same representative prompts, documents, or tasks so that their performance can be compared under similar conditions. The organization can examine whether each model produces relevant and accurate results, follows instructions, handles the required context, responds within an acceptable time, and operates at an acceptable cost. Where human usefulness matters, the people who will actually use the system should also participate in the evaluation. If the baseline performance is not sufficient, the organization can test whether prompting, grounding, retrieval-augmented generation, tuning, or other adaptations improve the results. The objective is to determine whether the model can consistently reach the required threshold rather than whether it occasionally produces an impressive answer. This leads to a useful selection principle. Choose the simplest model that consistently performs the required task well enough. A more capable model may still be appropriate where the workload genuinely requires that capability, but additional size and complexity should provide a measurable benefit. Model selection should also not be treated as a permanent decision. The generative AI environment continues to change rapidly. New models appear, existing models are updated, prices change, and workloads evolve. A model that is suitable during an early proof of concept may not be the most economical or appropriate model once the application reaches large-scale production. Organizations therefore need to think about model choice as part of a life cycle rather than as a one-time procurement decision. Applications should be designed where practical so that models can be compared, replaced, or routed according to changing requirements. We can now see why model selection begins with the workload. The organization identifies the task, defines the required quality and performance, considers the necessary context and modality, evaluates the trade-offs between large and small or general and specialized models, considers open and proprietary approaches, and then tests candidates against representative work. But choosing the model answers only one part of the deployment problem. Even the right model still has to run somewhere. It needs computing resources, memory, storage, data connections, serving capacity, monitoring security, and an environment capable of supporting the required workload. This brings us to an important distinction. Choosing the model and choosing the infrastructure are related decisions, but they are not the same decision. In the next section, we will examine where generative AI models can run, how cloud, self-hosted, hybrid, and on-device approaches differ, and what infrastructure is required to move a generative AI application from a successful experiment into reliable operational use. In the previous section, we examined how organizations can choose a generative AI model according to the requirements of the workload. We saw that the largest or most powerful model is not automatically the best choice, and that task fit, reasoning complexity, context length, modality, specialization, speed, cost, control, and deployment flexibility all influence model selection. But choosing the model solves only one part of the deployment problem. The model still needs an environment in which it can operate. It needs computing resources, memory, storage, data connections, serving capacity, monitoring, security, and an architecture capable of supporting the expected workload. This brings us to the second major architectural decision: where and how the model will run. Model choice and infrastructure choice are closely connected, but they are not the same decision. The model determines the kind of intelligence and capability available to the application. The infrastructure determines how that capability is delivered reliably, securely, and economically to users and business processes. A simple way to express the distinction is that the model answers the question, what intelligence do we need? Infrastructure answers the question, how will that intelligence be operated? For many organizations, the first infrastructure decision concerns where inference will take place. As we saw in the first video, inference occurs when a trained model processes a new request and generates an output. Every time a user submits a prompt, asks a question, uploads a document, or makes an application request, computing resources are required to perform that inference. There are several broad deployment approaches. A model may be accessed through a managed cloud service or application programming interface. It may be hosted on infrastructure controlled by the organization. Some workloads may use a hybrid architecture combining cloud and local systems, while others may run partly or entirely on a local device or at the edge. A managed cloud or API-based approach is often the fastest way to begin. The organization can access model capability without building and maintaining the complete underlying computing environment. Capacity can often expand as demand grows, and the provider assumes responsibility for much of the infrastructure management. This approach can be attractive when speed of deployment matters and when the organization does not want to maintain specialized AI infrastructure. It can also allow experimentation with several models before committing to a larger production architecture. But managed services introduce their own considerations. The organization may face recurring operating costs, dependence on provider availability and pricing, limitations imposed by the platform, and questions concerning where data are processed or stored. Data residency, privacy, contractual requirements, and vendor dependence may therefore influence whether this approach is appropriate. At the other end of the spectrum is self-hosted or organization-controlled infrastructure. Here, the organization operates the model within an environment over which it has greater direct control. This can be valuable where data sensitivity, customization, security, or regulatory requirements make greater control necessary. The organization may determine where information is processed, how access is managed, how the model is configured, and how the surrounding infrastructure is secured. Greater control, however, also creates greater responsibility. The organization must provide the required computing resources, specialist expertise, maintenance, monitoring, capacity planning, security, and system updates. Infrastructure that appears attractive from the standpoint of control can therefore become expensive or difficult to operate if the organization does not have the necessary technical capability. A hybrid approach combines elements of cloud and organization-controlled infrastructure. Sensitive data or selected workloads may remain within a controlled environment, while other processing can use scalable cloud resources. This can provide flexibility where different parts of the workload have different privacy, latency, or scale requirements. The trade-off is architectural complexity. Once a system spans several environments, the organization must manage data movement, interfaces, security boundaries, monitoring, and reliability across those environments. Hybrid architecture can therefore solve important problems while creating new operational requirements. A fourth approach is local, edge, or on-device inference. In this case, the model runs close to the user or the equipment generating the information. This can reduce data movement, improve privacy, allow operation without continuous network connectivity, and provide very low response times. These characteristics can be useful for real-time applications, mobile devices, industrial systems, or situations where information should not leave the device. But local deployment is constrained by available computing power, memory, energy, and model size. A compact model may therefore be necessary even if a larger cloud-based model could provide greater general capability. Once the deployment environment has been selected, the organization must consider the wider infrastructure stack supporting the application. The model is only one component of that stack. Computing accelerators provide the processing required for training or inference. Memory holds model parameters and active working information. Storage contains models, organizational data, logs, and other artifacts. Data pipelines bring information into the system, clean and transform it, and help maintain appropriate access and governance. If the application uses retrieval-augmented generation, retrieval infrastructure is also required. The system must be able to search or retrieve relevant external information and supply it to the model when a request is processed. Vector databases and other search technologies may therefore become part of the architecture. Networking connects the different components and moves information between users, applications, data sources, and computing resources. The serving layer receives requests, allocates inference capacity, and manages the number of users or application calls that the system can support at one time. Monitoring is another essential component. An organization operating a production generative AI system needs to know whether the application is available, whether response times remain acceptable, whether failures are occurring, which model version is being used, how much capacity is being consumed, and whether performance is changing over time. Security and governance also have to be built into this infrastructure. Access controls determine who can use the system and what information they can retrieve. Privacy and residency rules affect where data can be stored and processed. Monitoring and logging provide evidence of how the system is being used, while policies and technical controls help enforce organizational and regulatory requirements. The infrastructure decision therefore extends far beyond simply choosing a cloud provider or purchasing computing hardware. It involves the complete environment required to support reliable generative AI operation. Another useful distinction is between training infrastructure and inference infrastructure. Training develops or refines a model. Large-scale training can require tightly connected clusters of specialized processors, enormous computing capacity, substantial electrical power, advanced cooling, and very high-speed networking. Training frontier-scale models is therefore an infrastructure problem of a very different magnitude from the requirements faced by most organizations adopting generative AI. Inference is the more immediate issue for most users and enterprises. The model has already been trained, and the infrastructure must now serve requests from people or applications. These requests may arrive continuously and at different volumes throughout the day. Inference infrastructure must therefore support the responsiveness and reliability expected from a production service. If a customer service assistant is used by thousands of customers at the same time, the infrastructure must handle that demand without unacceptable delays. If the system forms part of an operational workflow, it may need high availability so that the business process does not stop when the AI service is unavailable. Several performance measures become important at this stage. Latency refers to how long the user waits for a response. Throughput refers to how much information or how many requests the system can process over time. Concurrency refers to how many users or application calls can be served simultaneously. Availability and resiliency concern whether the system remains accessible and how it recovers from failures. Context processing also affects infrastructure performance. A request involving a short prompt requires less processing than one involving several long documents. Multimodal inputs such as images, audio, or video can add further computational demands. The workload must therefore be understood not only in terms of how many requests are expected, but also in terms of how much processing each request may require. This is why model and infrastructure decisions cannot be made independently. A very large model may provide excellent capability, but require substantially more memory, computing resources, and serving capacity. A smaller model may support the same narrow workload with lower latency and lower operating cost. The correct architecture therefore comes from matching the model and infrastructure to the same set of workload requirements. Consider a general-purpose knowledge assistant used by a moderate number of employees. A managed cloud model may provide sufficient flexibility and allow the organization to deploy quickly without owning specialized infrastructure. Now consider a high-volume, narrow application performing millions of repetitive requests. A smaller or specialized model operating on cost-efficient serving infrastructure may produce a much better economic result. A sensitive domain application using proprietary records creates another set of requirements. Greater control over data, retrieval, deployment location, and security may justify a private cloud, hybrid, or self-hosted environment depending on organizational policy. A real-time application running on a device creates yet another architecture. Low latency, reduced data movement, and privacy may matter more than access to the largest available model, making a compact on-device model the more appropriate choice. The infrastructure should therefore be designed around the workload rather than around an abstract idea of maximum computing power. The objective is to provide enough capability, capacity, security, and reliability to perform the required work without introducing unnecessary complexity or cost. This also means that infrastructure requirements will change as an application moves from experimentation to production. A proof of concept may involve a small number of users and limited data. A successful production application may eventually serve thousands or millions of requests, operate continuously, connect to several enterprise systems, and require formal monitoring, resiliency, and support. Organizations should therefore test the complete architecture rather than the model alone. A model that appears fast during an individual demonstration may behave differently under heavy concurrent demand. A system that is affordable during a small pilot may become expensive when request volumes increase substantially. This brings us to another major deployment issue: cost. Generative AI cost is not simply the advertised price of a model or the cost of a single API request. It includes inference volume, computing capacity, data storage and retrieval, networking, security, monitoring, specialist labor, and the infrastructure required to maintain reliable service. Data architecture must also be considered alongside cost. A powerful model cannot compensate for poorly organized, inaccessible, outdated, or weakly governed enterprise information. If a generative AI application depends on organizational knowledge, the quality and architecture of that data become part of the AI system itself. Security, compliance, regional availability, and governance can also eliminate otherwise attractive technical options before detailed testing even begins. A model or deployment environment that does not satisfy requirements for privacy, data residency, licensing, or organizational security may simply be unsuitable regardless of its capability. The infrastructure decision therefore leads naturally to a broader question. Once the model and deployment environment have been selected, how do we determine the complete cost of operating the system? How do we prepare the data it depends on? And how do we ensure that the architecture remains adaptable as models and workloads change? In the next section, we will examine the move from pilot to production economics. We will look at total cost, data architecture, security and compliance gates, the use of multiple models, and why generative AI systems must be designed for change rather than treated as fixed technical investments. In the previous section, we examined the infrastructure required to operate generative AI. We saw that model choice and infrastructure choice are related but different decisions, and that organizations must consider where inference will run, what computing and memory resources are required, how data will be stored and retrieved, how requests will be served, and how the complete system will be monitored and secured. These questions become particularly important when an application moves beyond experimentation. A proof of concept may involve only a small number of users, a limited collection of documents, and relatively few model requests. A production application may eventually serve thousands or millions of interactions, operate continuously, connect with several enterprise systems, and require formal security, monitoring, support, and reliability. This transition from pilot to production changes the economics of generative AI. The relevant question is no longer simply whether the model can perform the task. The organization must determine whether the complete system can perform that task repeatedly at the required scale and at an acceptable total cost. This brings us to an important principle. The cost of generative AI must be evaluated end to end. The advertised price of a model, or the cost of an individual API request, represents only one part of the total system cost. A production generative AI application may also require computing capacity, storage, data pipelines, retrieval systems, networking, monitoring, security, specialist engineering, and additional capacity to cope with periods of high demand or system failure. Model usage itself can vary substantially according to the workload. A short prompt followed by a short response consumes less processing than an application that repeatedly sends long documents, retrieves large amounts of contextual information, performs complex reasoning, or generates lengthy outputs. Multimodal applications involving images, audio, or video can introduce further processing requirements. This means that the economics of a generative AI application must be calculated against the expected production workload rather than against a demonstration prompt. Consider two very different applications. The first is a specialist research assistant used occasionally by a small number of highly skilled professionals. Each request may be complex, involve long documents, and justify the use of a more capable and expensive model because the value of each successful analysis is high. The second application may generate millions of relatively simple customer responses. Even a small difference in the cost of each inference can become substantial at that scale. A smaller or specialized model may therefore provide a better economic result if it can perform the required task reliably. The cheapest model is not necessarily the lowest cost solution, and the most expensive model is not necessarily uneconomical. The relevant measure is the relationship between the quality required, the volume of work, the infrastructure needed, and the business value produced. Organizations therefore need to think in terms of total cost of ownership. Model or inference charges form one component, but data ingestion, cleaning, storage, and retrieval also create cost. Retrieval-augmented generation may require search or vector database infrastructure. Networking and data transfer add further requirements, while monitoring, security, observability, and specialist engineering must continue throughout the life of the application. Where infrastructure is owned directly, hardware investment, maintenance, depreciation, replacement, power, and capacity planning also become relevant. Where cloud services are used, some of those capital requirements are converted into recurring operating expenses, but the organization still has to manage consumption and understand how costs change as usage increases. Cost therefore cannot be separated from architecture. A technically successful pilot can become economically unattractive if it depends on an unnecessarily large model, sends excessive context with every request, retrieves more information than is required, or uses an expensive architecture for work that could be performed more efficiently. This is one reason optimization becomes important as an application matures. An organization may initially use a powerful general-purpose model to establish whether the use case works. Once the workload is better understood, it may find that a smaller model, a specialized model, improved prompting, fine-tuning, retrieval-augmented generation, distillation, quantization, or another architectural change can provide similar performance at lower cost. The model used for experimentation, therefore, does not have to become the permanent production model. The same principle applies to data. A production generative AI application depends not only on model capability, but also on the quality and organization of the information supplied to it. A powerful model cannot compensate indefinitely for weak data foundations. This is especially important when generative AI is connected with organizational knowledge. The information may be distributed across documents, databases, applications, shared folders, websites, and other systems. Some of it may be current, while other material may be outdated. Different versions of the same policy or procedure may exist, and access may need to vary according to the user's role. The organization therefore needs to determine who owns the data, who is permitted to access it, how its quality is maintained, how changes are recorded, where it is stored, and how the AI application retrieves the correct information. If retrieval-augmented generation is used, this data architecture becomes part of the generative AI system itself. The retrieval component must identify relevant information, provide it to the model, and do so within the security and access rules established by the organization. A failure in such a system may therefore have several possible causes. The model may have generated an incorrect interpretation, but the problem may instead have begun earlier because the retrieval system selected the wrong document, because the underlying information was outdated, or because the organization's data had not been organized effectively. Production deployment must therefore treat data architecture as part of AI architecture rather than as a separate issue that can be addressed later. Security, privacy, regulation, and compliance create another set of constraints. These considerations should not simply be added after a model and infrastructure have already been selected. In many cases, they should operate as early selection gates. An organization may discover that an otherwise attractive model or deployment environment cannot be used because prompts or documents would be processed in an unacceptable location. A regulated activity may require information to remain within a particular jurisdiction or controlled environment. Licensing terms may restrict how a model can be used commercially. Organizational security standards may require levels of access control, logging, monitoring, or incident response that a particular service cannot provide. These requirements can eliminate technical options before detailed performance testing even begins. The relevant questions include where prompts, documents, retrieved information, and generated outputs will be processed and stored, whether sensitive data can remain within an approved environment, whether the platform satisfies enterprise and regulatory security requirements, whether the licensing conditions are compatible with the intended use, and who is responsible for guardrails, updates, safety controls, and incident management. These are not peripheral questions. They determine whether the system can be deployed at all. Another important development is that a generative AI application does not necessarily have to rely on a single model. Different requests may require different levels of capability. A simple, low-risk task may be handled efficiently by a smaller and cheaper model, while a more complex or consequential request may be routed to a more capable model. This creates the possibility of model routing. Instead of making one permanent model choice for every interaction, the application can determine which model should handle a particular request according to factors such as task complexity, cost, latency, or risk. A workflow can also use several models for different stages. One component may retrieve information, another may perform reasoning, another may generate the final response, and another may support tool use or specialized processing. This can improve flexibility and cost performance, but it also increases architectural complexity. The organization must be able to observe which model handled which request, understand how the components interacted, diagnose failures, forecast cost, and ensure that routing decisions remain consistent with organizational controls. Model choice can therefore become a runtime decision rather than a permanent design decision, but only if the architecture remains understandable and governable. This leads to another important principle. Generative AI models and infrastructure have life cycles. The technology is changing rapidly. New models appear, existing models are updated or withdrawn, pricing changes, context windows expand, capabilities improve, and new deployment options become available. At the same time, the organization's own workload may change as more users adopt the application or as the system becomes connected with additional information and business processes. A model that was appropriate during the proof of concept stage may therefore not remain the best choice in production. The application may eventually need a different model because of cost, performance, security, availability, or new requirements. Organizations should consequently avoid designing systems that make model replacement unnecessarily difficult. Where practical, applications can use abstraction layers and consistent interfaces so that candidate models can be tested in parallel and replaced when a better option becomes available. Changes should themselves be evaluated. Replacing one model with another may alter quality, latency, cost, tone, instruction following, safety behavior, or the way the system uses context. A new model should therefore be tested against the same representative workload before it replaces an existing production system. Infrastructure must also be able to evolve. A pilot may run successfully with modest serving capacity, but production use may require additional compute, storage, retrieval capacity, monitoring, resiliency, and network performance. Organizations should therefore plan not only for the system they need today, but also for how the workload may grow. At very large scale, physical infrastructure becomes another part of the economics. Frontier model training and hyperscale AI operations depend on high-density computing, substantial electrical power, advanced cooling, high-speed networking, and resilient data center capacity. These challenges are primarily faced by hyperscalers and organizations operating very large AI infrastructure rather than by the typical enterprise using a managed AI service. For most organizations, these physical requirements are consumed indirectly through cloud or model service providers. But they remind us of an important underlying reality. Generative AI is ultimately a computational system that depends on physical infrastructure, and increased AI usage has real consequences for capacity, energy, cost, and system design. The move from pilot to production therefore requires a broader view than simply asking whether a model produces good answers. Organizations must consider the expected workload, total cost of ownership, data architecture, security and compliance requirements, model routing options, and the ability to change models and infrastructure as the system evolves. A practical deployment sequence begins with the business problem and workload requirements. The organization applies governance and security constraints, shortlists appropriate models, determines where inference should run, assesses the supporting infrastructure, estimates the likely production cost, and tests candidate models on representative work. The full architecture can then be piloted under realistic conditions. Quality, latency, throughput, reliability, cost, and business outcomes can be measured, weaknesses identified, and the architecture optimized before wider deployment. This sequence can be expressed as a progression from business problem to workload requirements, model, deployment, infrastructure, evaluation, pilot, and finally scale. But one step in that sequence requires much deeper attention. Before an organization can decide that a generative AI system is ready for production, it must determine whether the system actually performs its intended task with sufficient quality, reliability, safety, and business appropriateness. That cannot be established simply by looking at a few impressive outputs, and it cannot be determined solely from public model benchmarks. Generative AI requires a more systematic approach to testing. In the next section, we will examine generative AI evaluation. We will look at what should be evaluated, how evaluation criteria are defined, how test datasets and rubrics can be created, and why different systems such as individual models, retrieval-augmented generation applications, AI agents, and enterprise applications require different forms of evaluation. Produce several plausible responses to the same request. Their outputs may be open-ended, context-dependent, probabilistic, and difficult to judge through a simple right or wrong test. An answer may sound fluent and still be incomplete. It may follow the requested style, but contain an unsupported claim. It may retrieve relevant information, but interpret it incorrectly. It may perform well on most routine examples and fail precisely on the difficult cases that matter most in practice. For this reason, evaluation cannot simply consist of looking at several outputs and deciding that they appear satisfactory. The objective is to move from informal judgment toward a repeatable, evidence-based process in which the system is tested against clearly defined requirements. The first step is to identify what is actually being evaluated. This may sound obvious, but the answer changes as generative AI systems become more complex. At the simplest level, the object of evaluation may be a single model response. The question is whether the model followed the instruction and produced a useful, safe, and appropriate answer. If the application uses retrieval-augmented generation, the object becomes more complex. The system must first retrieve relevant information and then generate an answer from that information. A poor result may therefore arise because the wrong source was retrieved, because the correct source was retrieved but the model interpreted it badly, or because the final answer was not sufficiently grounded in the information provided. An AI agent introduces another level of complexity. An agent may not simply generate a response. It may plan, select tools, retrieve information, interact with applications, and perform a sequence of actions before producing a final result. Evaluation must therefore consider not only whether the final answer was acceptable, but also whether the path taken to reach that answer was sensible and safe. An enterprise application creates still another evaluation target. The question is no longer merely whether the output looks good in general. The system must perform according to the requirements of the organization, profession, or regulated environment in which it will be used. A useful way to understand the progression is that a simple model response is evaluated mainly for the quality of the answer. A retrieval-augmented generation system must be evaluated for retrieval as well as generation. An agent must be evaluated for the answer and the sequence of actions taken to produce it. An enterprise application must additionally satisfy organizational, professional, security, regulatory, and business requirements. Once the evaluation target has been identified, the next question is, what should be measured? There is no single universal metric that determines whether a generative AI system is good. The appropriate criteria depend on the task and on the consequences of failure. Instruction following is one important dimension. Did the response actually satisfy what the user or application requested? A system may provide an intelligent answer and still fail if it ignores the required format, length, constraints, or task instructions. Quality and usefulness are broader measures. Is the response coherent, relevant, understandable, and usable for the intended purpose? The meaning of quality changes according to the task. A creative writing application, a coding assistant, and a legal document review system require very different forms of quality. Safety is another dimension. Does the system avoid behavior that has been defined as unacceptable for the application? The relevant risks depend on the environment and may include harmful content, inappropriate disclosure, unsafe recommendations, or actions that exceed the authority granted to the system. Groundedness, sometimes described as faithfulness, becomes especially important when a system is expected to answer from supplied or retrieved information. The question is whether the generated response is supported by the available evidence rather than introducing information that was not contained in the relevant source. Answer relevance asks a simpler but equally important question. Did the system actually answer what was asked? A response may be factually correct yet fail because it addresses a different issue or provides information that does not help the user complete the intended task. Factual accuracy considers whether the statements or computed results are correct. Completeness considers whether important information required by the task has been omitted. For enterprise applications, however, these generic measures may still be insufficient. An organization may require the system to comply with industry regulation, follow internal policies, preserve a particular brand or communication standard, handle restricted information correctly, and respect business rules governing what should or should not be said or done. Evaluation, therefore, becomes use case specific. The real question is not whether a model is good in the abstract. It is whether the system is fit for the purpose for which it is being deployed. Consider a customer service assistant that answers questions from approved company policies and product information. The organization may define success by requiring every answer to be factually correct, grounded in approved information, polite, concise, and consistent with company policy. Those requirements can then become evaluation criteria. The organization can test whether the answer contains unsupported claims, whether it uses the relevant policy correctly, whether its tone is appropriate, whether it follows the requested instructions, and whether all essential information has been included. This illustrates another important concept in generative AI evaluation: the use of rubrics. A rubric converts a requirement into an explicit test. Instead of saying that an answer should be good, the evaluator defines what good means for the task. Some rubrics can remain the same across every example. A customer service application may require every response to be professional, avoid restricted information, and remain within a specified length. These criteria can be applied consistently across the evaluation set. Other criteria may need to change according to the particular prompt. Suppose a prompt asks for a 4-sentence optimistic summary of a report. The evaluator can separately test whether the output is actually a summary, whether it contains 4 sentences, whether it reflects the report accurately, and whether the requested tone has been maintained. This makes otherwise subjective requirements more explicit and testable. But evaluation requires more than criteria. It also requires a set of realistic examples against which the system can be tested. This is the role of an evaluation dataset. An evaluation dataset should represent the actual use case rather than an artificial collection of easy examples. It may contain common prompts, representative documents, known correct answers where those exist, real examples from users, and difficult or failure-prone situations. Edge cases are particularly important. A system may perform extremely well on routine requests and fail when information is ambiguous, contradictory, incomplete, sensitive, or unusual. If these cases matter in production, they should appear in the evaluation dataset. For specialized enterprise applications, subject matter experts become particularly valuable. The organization can ask experienced professionals what characteristics they use when deciding whether an answer is acceptable and then incorporate those standards into the evaluation criteria. This helps ensure that evaluation reflects the actual work rather than merely generic measures of language quality. Once the dataset and criteria have been defined, several methods can be used to score the results. Some tasks allow computation-based metrics. If an output can be compared mechanically with a known reference or expected answer, deterministic measures can provide efficient and repeatable scoring. But many generative AI outputs are open-ended. There may be several acceptable ways of writing a response, explaining a concept, or summarizing information. In these cases, exact matching may tell us very little about actual quality. Human evaluation, therefore, remains important. People, especially subject matter experts, can assess qualities such as nuance, professional appropriateness, completeness, safety, usefulness, and whether the response would actually be accepted in real work. The limitation is scale. Expert evaluation can be expensive and time-consuming when thousands or millions of outputs must be assessed. This has led to increasing use of another language model as an evaluator, often described as an LLM as a judge or automated evaluator. The evaluator receives the generated output together with criteria or a rubric and assigns a score or judgment. This can make large-scale evaluation much more practical, especially for open-ended outputs that are difficult to assess through conventional metrics. But it creates a new problem. If one AI model is judging another AI model, how do we know whether the judge itself is reliable? The evaluator therefore has to be evaluated. A useful method is to assemble examples that have already been rated by trusted human experts and then compare the automated evaluator's judgments with those human assessments. Where the AI evaluator consistently disagrees with expert judgment, its rubric, instructions, model, or scoring method may need to be revised. Human judgment therefore remains the reference point for validating important automated evaluation systems. The evaluation process can now be assembled into a practical workflow. The organization first defines the use case and decides what capability, behavior, or risk needs to be evaluated. It identifies whether the target is a model response, retrieval augmented generation pipeline, agent, or complete enterprise application. It then creates an evaluation dataset reflecting realistic inputs and important edge cases. Metrics, rubrics, acceptance criteria, and ground truth answers are defined where appropriate. The system generates outputs for the evaluation examples, and those outputs are scored using automated metrics, human reviewers, AI evaluators, or a combination of methods. The results are then inspected at 2 levels. Aggregate scores help identify overall performance, while individual failures reveal where and why the system breaks down. This distinction is important because a single overall score can hide serious weaknesses. A system that succeeds in 95% of cases may appear excellent, but the remaining 5% may include exactly the situations where errors have the greatest consequences. Failure analysis therefore becomes part of the evaluation process. If an answer is poor, the organization needs to determine what caused the failure. The problem may lie in the prompt, model, retrieval system, source information, tuning, workflow, or another component. The relevant component is then changed, and the same evaluation is run again. Evaluation therefore becomes a feedback loop rather than a final examination. This principle becomes particularly clear with retrieval-augmented generation. Suppose an employee asks an internal assistant a question about company policy and receives an incorrect answer. Looking only at the final response does not tell us what went wrong. The retrieval system may have failed to find the relevant policy. It may have found an outdated version. The correct policy may have been retrieved, but the model may have misinterpreted it. The generated answer may also have included unsupported information that was not present in any retrieved document. A RAG system should therefore be evaluated at several points. Did retrieval find the relevant material? Is the final response grounded in that information? Does the answer address the user's question? Did the model interpret the retrieved content accurately? Evaluation of AI agents requires a similar expansion of the evaluation target. An agent may select tools and perform several actions before completing a task. The final answer may appear satisfactory even though the route taken was inefficient, unnecessary, or unsafe. The evaluator may therefore ask whether the agent selected the correct tool, whether it used that tool at the appropriate time, whether the sequence of actions was logical, whether it stayed within its permissions, and whether the final result was factually accurate and complete. The distinction can be summarized simply. For a basic generative AI response, evaluate the answer. For a RAG system, evaluate retrieval and the answer. For an agent, evaluate the answer and the path taken to produce it. Enterprise evaluation adds another layer because public benchmarks do not necessarily answer the question that matters to an organization. A model may rank highly on general tests of reasoning, coding, or language performance. That can be useful when comparing broad capability, but it does not establish that the model will behave correctly within a particular business process. An enterprise may require compliance with internal rules, regulatory obligations, confidentiality requirements, professional standards, and organizational conventions that are absent from public benchmarks. The organization's own acceptance criteria therefore become the decisive test. The important question is whether an experienced and accountable professional would regard the output as acceptable for the intended task. This is also why evaluation should not occur only once before deployment. Generative AI systems change continuously. Prompts are revised, models are updated or replaced, retrieval sources change, organizational data change, new tools are connected, workflows evolve, user behavior changes, and real production use reveals failure patterns that may not have appeared during testing. Evaluation should therefore continue throughout the generative AI lifecycle. During prompt development, evaluation can compare which instruction produces more reliable behavior. During model selection, the same test set can be used to compare candidate models. When migrating to a new model version, evaluation can reveal changes before the production system is switched. When a model is fine-tuned or customized, evaluation can determine whether the adaptation actually improved the intended behavior. During retrieval-augmented generation development, evaluation can help identify whether failures arise from retrieval, generation, or integration. During agent development, evaluation can examine tool selection and action sequences. After deployment, production examples should continue to be sampled and tested. Important real-world failures can then be added to the evaluation dataset so that future versions of the system are tested against problems that have already occurred. Evaluation therefore becomes a continuous development process. The system is defined, tested, measured, diagnosed, improved, retested, and monitored as it evolves. This leads to one of the central lessons of generative AI deployment. A successful demonstration is not proof of a dependable system, and a high benchmark score is not proof that an application is suitable for a particular organization. What matters is whether the system performs its intended task with sufficient quality, safety, reliability, and business appropriateness under the conditions in which it will actually operate. That conclusion brings together much of what we have examined throughout this video. Effective deployment begins with the use case. The workload determines what capabilities are needed. Those requirements influence model and infrastructure choices. Data, security, cost, and organizational constraints shape the architecture further, while evaluation determines whether the resulting system can actually meet the required standard. In the final section, we will bring these elements together into a practical deployment sequence and examine the transition from technological possibility to dependable operational use. Alone. It depends on the relationship among the use case, the workload, the model, the data, the deployment environment, the surrounding infrastructure, the evaluation process, and the people responsible for reviewing and using the system. This gives us a practical way to think about generative AI deployment as a whole. The process begins with the business problem or professional objective. Before selecting a model, building an application, or investing in infrastructure, the organization must identify what it is trying to improve. The objective may be to reduce the time required to prepare documents, help employees find organizational information, accelerate software development, improve customer service, support research, personalize communication, or perform another clearly defined task. The next step is to translate that objective into workload requirements. What must the system actually do? What kind of information will it receive? What kind of output must it produce? How complex is the reasoning involved? How much context must be processed? Does the task involve text alone, or does it also require images, audio, video, or other forms of information? The organization must also determine how accurate and reliable the output needs to be, how quickly the application must respond, how many users or requests it must support, and what happens if the system makes a mistake. These requirements create the basis for model selection. Instead of choosing a model because it is the largest, newest, or most popular, the organization can ask which model possesses the capabilities needed for the workload. Some tasks may require the broad capabilities of a large general-purpose foundation model. Others may be performed more efficiently by a smaller or more specialized model. A narrow, repetitive activity performed millions of times may place much greater importance on latency and unit cost than an occasional high-value analysis requiring complex reasoning. The organization must also decide whether it needs the flexibility and control offered by an open model, the managed services and commercial support associated with a proprietary model, or a combination of both. But the model still represents only one component of the solution. The next decision concerns deployment and infrastructure. The system may use a managed cloud service, run on infrastructure controlled by the organization, combine cloud and local resources in a hybrid architecture, or operate partly on a device or at the edge. The appropriate choice depends on factors such as privacy, latency, scale, technical capability, data residency, cost, and the degree of control required. The supporting infrastructure must then provide the computing resources, memory, storage, data pipelines, retrieval systems, networking, serving capacity, monitoring, security, and resilience required for the workload. Data becomes especially important when the application must work with organizational or current information. A powerful foundation model does not automatically know the latest internal policy, customer record, technical procedure, or business document. That information must be made available to the application through appropriate data architecture, retrieval systems, or other forms of integration. The quality of the generative AI system therefore becomes partly dependent on the quality of the information environment around it. Outdated, fragmented, inaccessible, or poorly governed data can create poor results even when the underlying model is highly capable. Security, privacy, regulation, licensing, and organizational governance must also influence architecture from the beginning. They should not be treated merely as controls added after technical development has been completed. A model or platform may appear ideal in terms of capability and cost, but still be unsuitable if it cannot satisfy requirements governing sensitive information, data residency, access control, licensing, or regulatory compliance. Once these constraints have been applied, candidate models and architectures can be tested on representative work. This is where evaluation becomes part of deployment rather than a separate final step. The organization can compare candidate models using the same prompts, documents, tasks, and acceptance criteria. It can measure quality, factual accuracy, groundedness, instruction following, latency, cost, user acceptance, and other dimensions that matter for the use case. The complete architecture can then be piloted under conditions that resemble actual use. Instead of asking only whether the model can produce a good answer, the organization can examine whether the system performs reliably particularly when connected with real data, retrieval systems, users, workflows, and infrastructure. This may reveal that the model is not the source of the main problem. Retrieval may be weak, data may be incomplete, prompts may need improvement, infrastructure may produce excessive latency. Users may find the workflow inconvenient. Security requirements may make parts of the original architecture impractical. Deployment is therefore an iterative process. The organization defines the problem, selects an initial architecture, tests it, identifies weaknesses, improves the relevant components, and tests again. Cost must be examined throughout this process. A pilot involving a few users may appear inexpensive, while the same architecture operating at production scale may require substantial inference capacity, storage, retrieval, infrastructure, networking, monitoring, security, and specialist support. Production economics may therefore lead to changes in the architecture. A smaller model may replace the model used during the proof of concept. Model routing may direct simple tasks to lower-cost models and more complex tasks to more capable ones. Retrieval may reduce the need to place large quantities of information into every prompt. Fine-tuning, distillation, quantization, or other approaches may improve the relationship between performance and cost. The objective is not to preserve the original architecture. It is to produce a system that performs the required work at an acceptable level of quality, reliability, cost, and risk. This also means that deployment does not end when the application enters production. Models change. Providers release new versions. Prices change. Organizational information changes. Users discover new ways of interacting with the system. New failure cases appear. Regulations and security threats evolve, and the workload may grow beyond what was originally expected. Generative AI systems must therefore be designed for change. Evaluation must continue after deployment. Important production failures should become new test cases. New models should be compared with existing ones before migration. Changes to prompts, retrieval systems, data, or workflows should be measured rather than assumed to be improvements. The deployment process can therefore be represented as a practical sequence. The organization begins with the business problem, translates it into workload requirements, selects an appropriate model, determines the deployment environment, builds the supporting infrastructure, performs systematic evaluation, conducts a realistic pilot, and then moves towards scale where the evidence justifies doing so. This sequence captures the central lesson of this video. Using generative AI successfully is not simply a matter of obtaining access to artificial intelligence. It is a systems design problem. The model matters, but so do the information supplied to it, the infrastructure supporting it, the workflow in which it operates, the cost of running it, the criteria by which it is evaluated, and the people who remain responsible for its use. This explains why the same foundation model can produce very different organizational outcomes. One application may remain a useful individual productivity tool. Another may become an internal knowledge assistant connected to organizational documents. A third may be embedded within a customer service process. A fourth may support software development, scientific research, or a specialized professional workflow. The underlying model may provide the generative capability, but the surrounding system determines how that capability is applied. Throughout this video, we have therefore moved progressively from use to deployment. We began by examining the 5 broad ways in which generative AI can create value: creating content, assisting and automating work, building software and digital products, analyzing information and supporting decisions, and engaging or personalizing communication. We then examined the 2 principal adoption routes. Generative AI can be used through existing applications, or it can be integrated and customized more deeply around organizational data, software, workflows, and business processes. We saw why the use case must come before the technology, and why model selection should be based on task fit rather than popularity or size. We then separated model choice from infrastructure choice and examined cloud, self-hosted, hybrid, and edge deployment, together with the wider infrastructure required for reliable inference. From there, we examined the economics of moving from pilot to production, the importance of data architecture, security and compliance constraints, the possibility of using multiple models, and the need to plan for changing models and infrastructure over time. Finally, we examined evaluation and saw why generative AI applications must be tested against realistic tasks and explicit acceptance criteria rather than judged simply by whether individual outputs appear impressive. Taken together, these elements provide a practical deployment framework. Successful generative AI deployment requires alignment among the use case, model, infrastructure, data, evaluation, cost, controls, and human expertise. But even a carefully designed and evaluated generative AI system has limits. Generative models remain probabilistic. They can hallucinate, reproduce bias, provide incomplete or inconsistent answers, and behave differently as information, prompts, models, and system components change. Enterprise deployment also introduces wider constraints involving data quality, monitoring, security, regulatory obligations, organizational readiness, and the difficulty of determining how much autonomy an AI system should actually receive. These issues take us beyond the question of how generative AI is deployed and toward a different question: under what conditions can it be trusted to operate? That is where we will begin in the next video. We will examine the operational limits of generative AI, the governance controls required to manage those limits, and the role of human oversight as AI systems become more deeply embedded in professional and organizational work. We will then look at real examples of human-AI collaboration and examine how work can be divided between machines and people according to their respective strengths. Because the objective of generative AI deployment should not simply be maximum automation. The more important objective is to determine where AI can add speed, scale, retrieval, generation, and analytical capability, where human expertise and judgment must remain in control, and how the two can be combined to produce a better and more accountable outcome.